All right, so let's take a quick look at practice midterm 1. As we can see with this first question, we are dealing with a discrete PMF. Now, does that mean that the PMF you see here will be on the actual test? You know, it probably won't, but it's to give you an insight and an understanding that one of the questions on the test will probably be a discrete PMF type question. In case it does not look completely familiar, you can recognize that P of X can also be written this way. X equals 1, 2, etc. So this is looking at the total number of trials until we hit the first success. In other words, X is geometric with parameter 1/2. All right, so that being said, let's first of all derive the MGF. All right, so deriving the MGF, mx of t, means we are going to find this expression. And finding this expression means we'll multiply e to the tx times px over the entire range of values of the random variable. In this context, this is going to be sum from x equals 1 to infinity of e to the tx. Our px is 1/2 to the x. And what's critical is to look at an expression like this and recognize and understand that what you want to do is bring the bases together so you have an expression that is essentially raised to the x power. Now this expression looks like a geometric series, right? And so a geometric series always ends up summing up to the first term over 1 minus the common ratio, provided e to the t over 2, the common ratio, is less than 1. All right, so that is our MGF, okay? We're going to use that MGF to go ahead and calculate, or I should say find and derive what our expected value is. We know that the expected value is the MGF evaluated at 0 once we take the derivative. Okay, and so what we'll do is we'll say that m sub x prime of t is equal to the derivative of that expression. Now what I'll do real quick is I'll just multiply the numerator and the denominator by 2, just so that I don't have a little fraction within a fraction situation. Okay, we can use the quotient rule. 2 minus e to the t, derivative of the numerator times the denominator, derivative of the denominator, times the numerator. Okay, so it looks like we'll get a little bit of cancellation with this and that. And so we just end up with 2e to the t over 2 minus e to the t. If we plug in 0 into that, we get 2e to the 0 over 2 minus e to the 0, which is 2 over 1, which is 2, our expected value. Not a surprise. We know that the expected value of this random variable is a reciprocal. All right, now for our variance, of course, we will need the second moment. Okay, so let's go ahead and identify the second moment first. That's going to be m sub x double prime of 0, right? Now, I won't go through all the motions, but suffice it to say, this is going to be 2e to the t, 2 minus e to the t squared. So a lot of chain rolling going on. 2t, 2 minus e to the t, all that divided by 2 minus e to the t raised to the 4th power. Plugged in, or I should say evaluated at t is equal to 0. This will end up being equal to 6. Okay, thus for the variance, v of x is e of x squared minus e of x quantity squared. It's going to be 6 minus 2 squared, which will also be equal to 2. All right, so that's the first question on this exam, showing what we have right here. We'll get the job done. All right, question number 2. What we're looking at is a joint PDF, and now we're looking at a continuous case. First things first, we want to identify whether or not the two random variables are independent, x1 and x2, given this PDF on this support. Now we have the theorem. If x1 and x2 are independent, we can write the joint as a product of marginals, right? But even more so, that's the definition. Even more so, the theorem said that we can kind of separate the joint into two pieces, which would look a little something like that. All right, so theorem is the way we want to go, not the definition in this case. But note, while the supports are separable, it's a rectangular support, which is a prerequisite to be independent. The joint, the functional part of the joint, is not separable. In other words, we cannot write it as a product of an x1 part and an x2 part. That being said, thus x1 and x2 are not independent. Okay. Alrighty. Part B. Let's find the CDF and use it to calculate this probability. All right, so to find the CDF, we want to look at how much probability is accumulated up to a given location. So I'm going to creep into part A space up here and draw a diagram of the support. Why, you may ask? Because that's what I do. I always recommend drawing a picture of the support when you're finding probabilities, especially. Sometimes expected values, but definitely probabilities. And so this is what we're looking at. We, for the CDF, know that f of little x1, little x2 is a probability that big X1 is less than equal to little x1 and big X2 less than equal to little x2. That's how much probability we've accumulated. All right, so what we're gonna end up doing is looking at this as a integration problem. Okay. All right, so this is gonna be equal to double integral of our density. Okay, I'll just go ahead and say dx1, or actually, okay, this is gonna be a double integral of our density, and I'll go ahead and say du dv, where u represents x1. So we'll start at 0 and go up to x1, and v represents x2. Start at 0 and go to x2. Okay, because we have x1 and x2 in our limits of integration, we must change the variable integration. So let me do the same thing over here. Let's call this u and v. Okay, so we want to express this as a double integral. But those are limits of integration involve x1 and x2. And so we have to integrate, of course, the PDF. But instead of x1, I'll put a u. Instead of x2, I'll put a v. And say du dv. U representing x1 starts at 0, goes to x1. V representing x2 goes 0, starts at 0 rather, goes to x2. Okay, so I'm integrating over a rectangular region within a rectangle. And so no need to, really think about the geometry too hard. This is exactly what's happening. So it's going to be an integral from 0 to x2 rather. Integral 0 to x1. And essentially we have u plus v. du dv. Okay, so when we integrate the u, we're treating v as a constant. Okay, so this will be the integral 0 to x2 of u squared over 2 plus uv, right, from 0 to x1 dv. Everywhere there's a u, we'll plug in x1. That's x1 squared over 2 plus x1 v dv. Do the same thing, work it out, and we end up with x1 squared x2 plus x1 x2 squared over 2. Nice and symmetric, right? That's on 0 less than x1 less than 1, 0 less than x2 less than 1. All right, so that's our CDF. Okay, and of course, we're going to be equal to 1 when we are beyond 1 on both of these variables, and equal to 0 when we're to the left of 0, right? Okay. And so what this is going to end up doing is allowing us to be able to calculate this quantity right here. Notice that quantity only deals with x2. So we're looking at the probability x2 is between 0.3 and 0.75. Okay. Okay, now if we look at that region here, x2 goes from 0.3 to 0.75. Okay, so we're looking at the space in between these two. Now, if I look at less than 0.75, that's down here, right? And what's x1 doing? x1 is less than 1 always. And so this is basically big F, how much I've accumulated when x1 is less than 1 and x2 is less than 0.75. That's the green zone. From that, I will subtract, let's say, use orange. I'm subtracting this. And the orange zone is F evaluated wherein x2 is less than 0.3. Now, x1 is also must be less than 1 in order for us to encapsulate this entire region to the left of 1, right? So we're looking at this difference. Each of these can be found by basically plugging into that piece right here. Okay. And then we get our answer through calculation. If I'm not mistaken, we end up with something like 0.46125.